Today you are going to study how to implement back propagation algorithm in MATLAB for XOR gate. So we have already discussed about back propagation algorithm. First you have to initialize weight randomly. So all weights should be initialized randomly and until the termination condition is met or till the error becomes zero or very small, you have to do the following step. For each training samples, we have to input the instant, means apply the input to the network and compute the network output. Okay. For each output unit k, we have to find this delta k, that is partial differentiation of E total with respect to this Wi, weight. For each hidden unit, we have to find delta H. For each network weight Wj, we have to find the new value of this weight using this delta rule. That is old value of weight minus alpha. Alpha is training rate being multiplied by del k or del H. Del k for uh, input layer, output layer, and del H for hidden layer. Now we'll write a program for this particular neural network. So we'll use this numbers only. This weight is not here. So we'll use this numbers only for weights and this bias. So B11 is biased to hidden node 1, H1. B21 is biased to H2. Then these weights have given number as 1, 1, 1, 2, 1, 3, then 2, 2, 2, 3. Here weights are 3, 2, 3, 3, and here W1. So these numbers only will use while writing a program in MATLAB. So first we'll give a input conditions. So uh, the 4 rows of truth table for XOR gate will be 0, 0, 0, 1, 1, 0 and 1, 1. These are written in the matrix form. Then the target output, we know the output for this particular input. If input is 0, 0, then output of XOR gate should be 0. For 0, 1 input, output should be 1. For 1, 0, output should be 1. And for 1, 1, output should be 0. So these are our target output. Once we train this network for this target output, then we can apply any input, so we should get a proper output. Then bias values, that is B11 and all these bias which I have shown in diagram, I have initialized here with -1. All three values are initialized with -1. Randomly we have to give this value. You can initialize with other values also. The learning coefficient, learning rate is considered here as 1. You can change it right by changing 0.5, zero point 0.6 like that. So the rate of learning depends upon this coefficient, that is alpha. The next is number of iteration. This number of iterations we can change and we can check the output whether we are getting proper output or not. If not, we can increase number of iteration. Here I am not comparing the error, but I am giving here the number of iteration. So you can start with the small value, check the answer. If it is not proper, increase the number of iteration till you get a proper output. Then weights, other weights, bias we have initialized with -1. So other weights also we have to initialize with random value. So here random values I have given for each weight. So total 9 weights are there in the diagram. So these weights are randomly initialized here. Any value you can give here. So for I is equal to 1 is to iteration. That means this many times we are going to execute all these steps to update the weights continuously. So for 1 is to iteration, the output vector we are defining, which will have initially 0. And since we are applying 4 set of inputs, we need a 4 output. So 4 rows will be there in output vector and 1 column. So initially we are initializing output with value 0. Then this num length parameter, it is the length of input, means how many inputs are there in input layer. So we are applying a 2 inputs. So this num length will be 2. Then for j is equal to 1 is to num length, that means 1 and 2, 2 inputs are there. So feed forward calculations will perform for each input. So H1 is equal to bias multiplied by weight plus second input, that is first input, that is 1 1, into the corresponding weight plus 1 2 second input into corresponding weight. So we are finding here H1 hidden layer output, and this hidden layer output we are passing through this sigmoid function. So this sigma function we are calling here, this should be written in separate .m file that we will discuss. So we are calling here sigma function, and we are passing this value of h1 output to this function, so that we will get an output of hidden layer 1 node. Then same for the second node of hidden layer H2, we are multiplying this bias by its corresponding weight. Then input is 1 1 multiplied by its weight, input 1 2 multiplied by its weight, and then this H2 is passed again through this sigmoid function, activation function, and we get this output X22 as the output of second hidden layer node. Then we calculate it for output layer. So output layer is having one output, that is denoted by X31. So it's bias into weight, then input, that is X21, output of hidden layer node 1 into its weight, output of hidden node 2 into its weight. So using this formula, we'll calculate the value of output layer. Again, it has to pass through sigmoid function. So we'll call this sigma function. We'll pass this value x31, and we'll get the actual output, that is outj. So these notations are given in a diagram of XOR gate. So from that you can check which weight we are multiplying by which bias or which input. Same notations are used here. So we got the actual output. Now we have to adjust the weight value. So for this, we'll first compute a delta. So for delta, the direct formula is used here. This formula is generally used to calculate this delta. So out j 1 minus out j multiplied by out j minus out j. So this out j is the actual output, and this is the target output, and this out j is the desired output or actual output. So this is for delta 3 1. Then this is at the output layer. We are uh, finding this error function and its partial derivative. Direct formula is used here. Similarly, to update the weights of hidden layer, we can use this formula, that is delta 2 1, and this is delta 2 2. This is for first hidden layer node, second hidden layer. So these direct formulas are used here to finding this delta. Now for weight calculation, now we are finding a new weight. So for that, this loop is used here. K varies from 1 is to 3. But if K is 1, then we are updating the weights of bias. So new weight for bias, that means 1 1 weight will be equal to weight 1 1 plus coefficient, that is learning rate we have considered as 1, into bias 1 1. that bias value and into this delta that is computed using error function. Then weight to 1, that is again related to this bias value. So to 1 because k is 1, weight to 1 plus coefficient, same formula is used here. For 3k, that is 3 1, same formula is used. So we are updating the weights related to bias. Then updating the weights related to other branches. So for that, if k is equal to 2, you will get updation of weight 1, 2. The formula, same formula is used here. Here the updation of weight 2, 2. Then here 3, 2. And when the k is 3, here you will get updation of weight 1, 3, 2, 3, and 3, 3. Same weight notations are shown on the diagram which we have seen first, the diagram of XOR gate. So we'll end all these loop. This updation of weight will continue iteration times, and after this iteration, all iterations are completed, we'll get a output, final output. So we can display this final output using this display function, DISP out. So whatever output we'll get after this training of neural network, that will be displayed here. We can check this weight also. So we can type here weight 1 1, weight 2 1, like that. So value of this weight can be also displayed. Updated values of weight we can observe. So for that we have to display all this weight. So this is the program which will train this neural network of XOR gate. Now we are calling a function, that is sigma function, uh, used as an activation function in our diagram. So we'll write this file also, function y is equal to sigma x. X is the parameter passed through to this sigma function, and we'll write here expression to find this sigmoid function, and this y value will be passed to our main program. Now let us see how this program works in MATLAB. So same program is written here. So here we have defined the output, that is target output. Input states are given. Four inputs we want to apply, we are going to apply. So we need a four outputs. These are the actual output. Bias we have initialized. The learning rate is 1. Iteration initially I'll give as a 6 iterations. Then random weights are assigned here. Then number of iterations time, we are updating this weight. We are computing the output in forward direction. Then we are updating the weights, and after updation of weight, continuously we are uh, executing this program. The sigma function is written here as the second dot m5. So this sigmoid function computation will be done using this program. Now, if we want to display weight, you can display it like this. Weight 1 1 if you want to display. I have assigned this to variable A. So A will give you the last updated value of weight 1 1. I will save this program and will execute this program. So now this is the updated weight value, but check whether the output is proper or not. So here we can observe that we are not getting a proper output. Expected output is 0, 1, 1, 0. But the output is not same as a, means actual output is not same as a target output. So we can increase number of iteration. So I'll increase iteration as 600. So let us check the output. This is the updated weight W11. All weights also you can observe. So this is the output. Again, it is not proper. For this input we are getting this output. So again we'll increase this equation. So now you can see that the output is approximately, the actual output is nearly equal to this targeted output. So if you increase this again, you may get the exact output.